Hi, my name is Andraž Krašovec, and today I will present our work on privacy-preserving IoT authentication systems based on adversarial learning. The title of our work is Opposing Data Exploitation, Behaviour Biometrics for Privacy-Preserving Authentication in IoT Environments. To kick off, let me tell you a story shedding some light on the problem we are addressing. Meet Alice. Alice is tired of constantly forgetting her passwords and decided she would like an authentication system that does its job without any interaction from her. And meet Carl. He has just the thing for Alice: a behavior-based authentication system supported by a variety of IoT sensor modalities. Alice likes the idea of utilizing less invasive biometric modalities that do not include techniques like facial recognition or fingerprints. However, she is still worried that Carl may abuse the collected data in some way. And she is not wrong. Besides providing an authentication services that alleviates the burden of traditional authentication systems, Carl would also like to model her behavior in order to sell her targeted ads. Therefore, Alice agrees to use Carl's system while setting an additional condition. Carl has to implement a filter that only passes through information related to user identification and obfuscates any other. In that way, he cannot recognize what Alice is doing at any given time. While of course not being overly thrilled about this condition, Carl then focuses his efforts into filtering data to remove activity information while still providing the best possible authentication solution. Before diving into the proposed method, let's define the scope of our work to prevent further confusion. In this paper, we perform a preliminary study on applicability of adversarial learning for privacy-retaining authentication systems. While we interchangeably use identification and authentication, we focus on user identification, meaning our goal is to accurately as possible predict the user's identity for a given input. Initial inspiration of our work is the Privacy Adversarial Network developed by Liu et al. In 2019. Taking a look at the image on the right, you can see that they utilize a 4-part neural network that can be used for a variety of tasks, including digit, image, voice, and human activity recognition. By utilizing adversarial learning, they train the encoder part of the network to obfuscate the data retaining users' privacy, as well as simultaneously retaining or even improving the classification accuracy. Most intuitive example is image recognition. As you can see on the images of the 2 school buses, PAN, the Privacy Adversarial Network, is able to render the images unrecognizable to humans while preserving the feature space relative for machine image recognition. Other approaches perform worse in either of the components, either failing to obfuscate the image enough not to be recognizable by a human, this is the privacy part, or obfuscating it in a way that hurts its overall classification accuracy, the utility part. We adapt the Privacy Adversarial Network in order to utilize it for user identification, utilizing behavioral IoT data. The architecture of the implemented network is shown in the bottom image. We apply some relevant modifications to fit the data we utilize. First, we remove the reconstructor part of the network, as multimodal sensor data cannot be intuitively interpreted by a human as an image can be. Of course, this has an additional benefit of not adding an additional computational complexity to the system. Furthermore, we add an additional LSTM layer to the encoder, as that way we are able to infer time sequence sensitive information that images do not benefit from, but proved to be a big boost for user identification accuracy. As we remove the reconstructor part of the network from the original Privacy Adversarial Network, we modify the training algorithm accordingly. Every epoch of the training algorithm is split into 3 steps, each considering a certain part of the system. We utilize categorical cross-entropy loss function in every step of the training. First step trains the legitimate flow of the information, which includes the encoder and user classifier parts of the network. It is mostly purposed to train the user classifier. Second step is considered with giving the activity or the adversarial classifier a best possible chance to discern between different activities given the information available for the encoder. Of course, to prevent training the encoder to pass through activity-relevant information, we lock trainable parameters of the encoder. Third and final step trains the complete system utilizing a weighted loss function, telling the encoder to let through user identity while filtering out activity-specific information. As the loss function of the activity classifier is negatively weighted, we lock its trainable parameters to prevent artificial damage to the accuracy of the activity classifier. The dataset we use contains sensor data from 15 different users and multiple sensor modalities, including the accelerometer, gyroscope, force, infrared, and Hall sensors. Additionally, we monitor the use of PC resources such as CPU, memory, and network usage. The participants of the user study were asked to complete different everyday office-like activities as demonstrated in the images. First activity includes copying a body of text from a cardboard card. In the second activity, participants browse the internet in order to find the weather prognosis of the place of their choosing and suggest some tourist attractions based on it. In the end, they have to send an email containing their suggestions. Last activity requires the user to first navigate a series of boxes placed around the environment to find the datasheet that they later used to generate a graph using any PC tool of their choosing. We recognize the limitation in the amount of gathered data as well as the low number of users. In the future, we plan to extend or collect a new dataset containing less convoluted activities. Observing the top right figure, we see an overall user identification accuracy of 79%, depicted as AAS. This result is much too low for a standalone authentication system. Nevertheless, it still outperforms baseline approaches like random forest and ADA-Boost, depicted as ADA and RF respectively. Additionally, we separately train a detached version of our system, which is depicted as DET. This system consists of the encoder and user classifier, and by that meaning that we remove the adversarial part of this network. And interestingly enough, it is not able to outperform our complete adversarial system. Focusing on the privacy aspect of our solution, we again compare the accuracy of our system to the same baseline approaches, including a detached version of the system. This time, the detached version of the system consists of the encoder and the activity classifier, as in this task, this is the data that we would like to predict. Again, the detached classifier is trained separately. Compared to the detached version, we achieve a 30% reduction of the activity recognition task, and at the end, we perform worse than even a majority classifier. That shows that our system is able to obfuscate activity-related information successfully. Furthermore, on the bottom figure, we observe a reduction in identification accuracy with a rising number of users. This presents a serious problem in authentication, as other approaches such as passwords or HUD biometrics do not suffer from this phenomenon. One thing we plan to investigate in the future is the use of personalized classifiers, which, besides mitigating the issue of more than a few users, also alleviates the need for retraining the system with inclusion of every new user. In conclusion, we devised a privacy-preserving system capable of simultaneously identifying users and obfuscating the user's current activity. There are a few directions we would like to explore in the future. One, of course, is to collect a new dataset that includes many more users that perform less complex activities. We also plan to include some new sensor modalities, such as short millimeter wave radar. As the identification accuracy of the system is low, we are considering exploration in continuous authentication, meaning that the user first authenticates via a more traditional mechanism, and then our approach monitors the whole duration of the session. A preliminary study we already performed shows a great potential in such approach. Lastly, as relevance of sensor modalities change with different user activities, we would like to also implement an attention mechanism. That's a mechanism similar to one that is used in transformers. And we would like to use it to automatically define sensor relevance at any given time step. That is all from my side. Thank you for your attention.